Hello everyone, this is going to be section 5.2 class problems. So the first question, we need to verify the basic step, state the inductive hypothesis, and state what would you need to prove the inductive step in problem 1. So essentially we're just verifying what are the pieces that we need to have for each of the step of induction. It's not necessarily asking me to fully prove, so that's what we're going to do at least in this question. So first, verify the basic step for this. So first, let's define who the property is. So the property of n is that 1 plus 3 plus 5 plus 2m minus 1 is equals n squared. So because this is saying that n is equals 1, well, I'm going to prove p of 1. So first, let's check the left side. So the left side is, of course, just 1. Up to, and it's 1 because it's 2 times 1 minus 1, right? And so this is essentially just 1. This will be what happens if I'm doing that. Now the right side is plug in n squared. 1 squared is just 1. So both sides, left side is equals to right side. So we had that the initial condition works. Now let's talk about the inductive hypothesis. So for some k that belongs to the integers, p of k is true, where p of k means that the sum from 1 plus 3 plus 5 plus 2k minus 1 is equals to k squared. So we have this as our hypothesis. What do we need to prove? Now we need to prove the step pk plus 1, which will be 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1 minus 1 is equals to k plus 1 square. So that's what I need now to prove in here. Okay? All right, so this is just verifying that we can state each of the pieces that we need to do. Indeed, we're not going to go and prove this one. I'm going to leave this one as an exercise for you. So let's prove some other things. All right, so for question number 4, we got to prove that for n bigger than 1, 2 plus 4 plus 6 plus up to 2n is equals n times n plus 1. So first, let's check the basics condition. So p of n is, of course, this. This is p of n, this condition. And p of 1 is going to be two sides. So on the left side, we have that this is just 2, right? Because it's the first element is 2. Or when n is equals 1, just is 2. And now the right side is 1 times 1 plus 1, which is also 2. So the left side is equals to the right side, and we have that the basic steps works. Now we're going to write the induction hypothesis. So for the induction hypothesis, we're going to assume let k that belongs to the integers. So 2 plus 4 plus 6 plus 2k is equals to k times k plus 1. Okay? So now we're assuming that this is true. And now we want to prove p of k plus 1. So what is p of k plus 1? Well, the left side of p of k plus 1 is that 2 plus 4 plus 6 plus 2k plus 2k plus 1 And then we're going to have that this is equals to k plus 1 times k plus 2. So this is what we want to show. Want to show that this is true. So let's prove it. So we'll start by saying, well, 2 plus 4 plus 6 plus 2k. So plus, plus, plus. Maybe we'll just write this correctly. Plus, plus, plus. 2k plus 2k plus 1 is what? Well, notice that this is p of k up to here. So this is just equivalent to p of k plus 2k plus 1. And so by hypothesis of induction, then we use the hypothesis of induction to say, oh, okay, so p of k is k plus 1. So this is equals to k plus 1, and then plus twice k plus 1. But if you see, we can just factor k plus 1 out of here, and then we get k plus 1 times k plus 2. And so we got it. We got what we wanted. So now I don't have the space to write this here, but you should write it when you have a chance. You say by the hypothesis of, by induction, by the method of induction, P of n is true for n bigger than 1. Okay? All right, let's go to number 5. So we want to prove by mathematical induction that the sum of the first n squares is n times n plus 1 times 2n plus 1 over 6. Okay, so first and nth, once again, this is P of n. We're going to prove the basis. And the basis case is just like 1 square, which is the left side, is equals to 1 plus 1, 2 plus 1 over 6. So this is 1, clearly. So this will mean that if I simplify this side, notice that I get 2 times 3, which is 6. 6 over 6 is 1. So we get 1 square, which is 1, equals 1. So we got it. We get our first step. Now the induction hypothesis will be, let k that belongs to the integers. So 1 square plus 2 square plus up to k square is k times k plus 1 over 2k plus 1 over 6. So we're saying that this works for this k. P of k is true. Now, we want to prove P of k plus 1, which is pretty much proving that the sum up to k plus 1, k plus 1 square, is going to be equals to what? We replace by k plus 1, so we get k plus 1, k plus 2, and here we will get 2k plus 1 divided by 6. Okay, whatever this is. I can simplify this, and this is going to be 2k plus 2 plus 1, so this is going to be 2k plus 3. Okay, now let's prove it. The left side is going to be 1 square plus 2 square plus k square plus k plus 1 square. Okay, the sum of the first k plus 1 square. But now this part, I know this is P of k. So this is P of k plus k plus 1 square. Now, P of k by hypothesis of induction is equals to k plus 1, 2k plus 1 over 6 plus k plus 1 square. Okay? So now we're going to take the opportunity to factor out 1k plus 1. So we're going to factor out k plus 1. And so we're going to put a 6 up and down here. So we get the same fraction. And so I'm going to, and now I'm going to factor the 6th as well. And now this is going to be left here, k times 2k plus 1 plus 6k plus 1. Okay? And so now we're going to simplify this little piece. Notice that this is going to be equals to k plus 1 over 6. And this, if I multiply all this, this is going to give me 2k squared plus k. And I get plus 6k from here, so plus 7k plus 6. Okay? And now I can factor this one out, and this is going to be k plus 1. And factoring out, this is going to be k plus 2 times 2k plus 3 over 6. So notice that that's the 2k plus 3 that I was expecting to get. So if you're wondering if this is true, you multiply again just to check. K by 2k, 2k squared. K by 3, 3k. And so 3k plus 4k, 7k, and then plus 6. So you can see that this works. So now we just got what we wanted to show. And so P of n is true for all n bigger than 1 by induction hypothesis. Okay? All right, so now let's move on to question 6. And question 6 is pretty much what I was trying to prove over here. So I'm going to skip the steps that I already did here, and I'm just going to go directly to the part where I'm going to prove the step k plus 1. So question 1 has basic case and induction hypothesis. Okay? So the k plus 1 case will be 1 plus 3 plus 5 plus 2k minus 1 plus 2k plus 1 minus 1. And now notice that once again, this is the pk part. And so this is going to be equals to just k squared plus, and then this piece, which I can see as 2k plus 2 minus 1. So I can see it as k squared plus 2k plus 1. Which if I factor this out, this is just k plus 1 squared. So now notice that I just show that for the k plus 1 step, this holds. So P of n true for n bigger than 1. Okay, so I'm gonna stop here, and in part 2, I'm gonna continue doing the rest from question 7 onward.